Hello and welcome back to CMOS RFIC circuits, CMOS RF integrated circuits. This is lecture 26. We were doing mixers, multipliers, that was our module 9, and what we have been talking about, we have basically developed a double balanced Gilbert cell mixer. This is a double balanced Gilbert cell mixer, and at the end of the previous class we were struggling to figure out how we can interchange the RF and the LO terminals, right. This is what we were struggling to figure out at the end of the previous lecture. So, we will finish with that, and then we are going to talk about mixer non-idealities. What are the different problems with mixers, how they are going to affect the radio architecture, and so on and so forth. All right. So, in the last class we ended it on the note that I can potentially move the LO to the layer of transistors on top, and I can move the RF to the layer of transistors on the bottom. So, if I have RF on top, LO at the bottom, no problem whatsoever, no problem at all. I have some matching issues. How do I match the RF signal that is coming from the LNA to the input of the mixer? The input of the mixer is looking like a capacitor. So, there is not going to be any power transfer at all. So, I can't do matching at all. So, that is problem number 1, right. Problem number 2 is maybe the capacitance is going to be too much, because there are now 4, you have to drive 2 sets of transistors, all right. So, that is why we wanted to move towards bring the RF to the bottom layer of transistors, the LO to the top layer of transistors, and this also works fine. The LO is a large signal that goes on and off, and I get this as my output. When the LO is high, I get the plus symbol over here, and LO is low, I get the minus symbol over here, all that is fine. The problem is that internally it is proportional to the square of, I am sorry, the difference of the 2 squares of VRF plus minus VT and VRF minus minus VT. So, if this relationship did not have the square term, if it had only a linear term, then I would be happy, right. Or rather you could also represent it as a plus b times a minus b, a square minus b squared is a plus b times a minus b, right. Now, this is okay if VRF plus is equal to minus VRF minus. So, if you can make sure that these two cancel out with each other, then this is okay, but if you can't make sure of that, if there is a common mode signal over there, then we are in trouble. Okay. So, in general it is going to be non-linear. So, we need to linearize this, and how do you linearize a circuit? So, think about this. You apply V in over here, small signal, and the output you get, if V in is a small signal, then the output is minus G m R parallel R d s times V in. Now, this works only if it is a small signal. If V in is a large signal, then G m itself is going to vary, which could be our case, right, and then we are in trouble. How do you linearize such a circuit? How would you linearize such a circuit? You introduce source degeneration, right. You put a load over here, and as soon as you do that, VGS, you can think of VGS as a small quantity, and the gain is no longer going to be controlled by GM. The gain is going to be something like R by RS, almost equal to this. Okay. This will work as long as RS is very large, RDS is very large, GM is large. You can easily conceive of this, and here this is irrespective of whether the input signal is a large signal or a small signal, right. This is the way we linearize. Now, you could also conceive of putting an inductor over there instead of a resistor. Even that is going to help you in terms of linearization. So, at DC there is going to be nothing, but at the high frequency that will present an impedance, and at that high frequency this is going to behave like a perfectly linear amplifier, right. So, this is the technique we are going to use. So, this is the technique we are going to use, and we can do this. We can in fact go a step further and join these two grounds and make it differential. That is going to reject the common mode signal, right. What else is that going to do? That will also give you a resistance looking into the gate of the mixer. You remember our LNA discussion, when I degenerate the source with an inductor, the input impedance of the LNA becomes resistive, and that is great because now I can do my matching, right. So, this is often done, and to first order you need not do it, because all you have to make sure is that the common mode of the RF signal is 0. So, if you do that, you are all set, or the common mode of the RF signal is a constant. You do that, you are all set, you do not have to do anything else. But for if you want to linearize it, get rid of the common mode signal, this is one way of doing it. Okay. The additional advantage that this gives you is that it helps you in terms of matching. Now, you get a resistive input as opposed to a pure capacitance. All right. So, this is as far as our mixer discussion goes. This is how we design mixers. We make a double balanced mixer. You are going to, for input matching purposes, you may or may not want to put that inductor over there, and you are done. The output of the LNA might not be differential. In fact, we did not design a differential LNA at all. if you look up the books, Thomas Lee's book, Razavi's book, there are examples of differential outputs for the LNA. So, you might want to check up what is in the books. You also might want to check up a few papers. There are a lot of low noise amplifiers which have a differential output. Typically, the input of the low noise amplifier is definitely going to be single ended, because there is only one antenna. There are some fussy designers out there who have not been able to make a single ended input for their low noise amplifier. They have made a differential low noise amplifier. They have had to have a balloon, a transformer, center tap transformer kind of structure at the output of the antenna to convert the single ended antenna signal to a differential balanced signal to the input of the LNA. Of course, the noise figure of the balloon, if it has any attenuation, it is going to hit you directly, because you are putting it in front of the LNA, right. So, it could be a fairly common strategy to have a single ended input, single ended output of the LNA, which means that you have put a signal only to VRF plus and VRF minus is hanging around at 0 volts or at the common mode voltage, which means that you are unable to pay attention to the common mode signal of VRF plus VRF minus, which means that it will be necessary for you to do linearization, which means that you might want to put some inductors over there for source degeneration and linearization at the same time. All right. Now, what are the non-idealities of this mixer? The first important thing to understand is isolation between the two inputs of the mixer. So, what you see over here is that the two inputs of the mixer are really gates of two different MOSFETs. So, VRF plus, there could be a parasitic capacitance between these two nodes. There could also be a parasitic capacitance between these two nodes, they are there, CGD and CGS are there, they exist, okay. There is no denying the fact, which means that a portion of VRF could potentially enter through the LO terminal, or a portion of the LO could potentially enter through the RF terminal. Right? It is conceivable that this happens. Now, does it create any problems as far as we are concerned? If a portion of I am going to call this IF, intermediate frequency. For a general heterodyne receiver, this is the intermediate frequency, right. Let us call it IF. So, let us first try to understand this. Let us say, let us take an example. Let us say that the RF is at 1 gigahertz and the LO is also at 1 gigahertz, which means I really want DC at the output. This kind of a mixer would be part of a direct down conversion receiver. Okay. So, one step single shot direct down conversion receiver, also called a homodyne receiver. Alright. You could also think of the scenario where, as far as the transmitter is concerned, this is on the Rx path. As far as the transmit path is concerned, you could think of a baseband signal, you could modulate it directly with the LO signal, and you could get 1 gigahertz at the output. This is a direct up conversion transmitter, homodyne, that is the word. Alright. So, let us think of both of these. Suppose the local oscillator leaks into the RF signal. What is going to happen? What is going to happen? You are going to get an extra component at DC. So, you are going to get LO times the LO at DC. Alright, think of it this way. Suppose the signal you are receiving from the antenna, is something at 1 gigahertz with 20 kilohertz bandwidth. This is the bandwidth around 1 gigahertz, and the signal level is minus 100 dBm. Okay, what is dBm? dBm is decibels with respect to 1 milliwatt of power. Okay. So, that is the power level that you have received at the input of your antenna. Now, from the input of the antenna, of course, there is the LNA gain, etc., etc. Let us say the LNA has a gain of 20 dB. So, you have got minus 80 dBm at the mixer input. Now, at the LO terminal, you are generating something which is a perfect tone at 1 gigahertz, but has a power level of 0 dBm. Okay. And let us say that because of the leakage, this is not a direct path, this is a leakage path, right. There is some capacitive division, etc., and because of that, when part of the local oscillator leaks into the RF terminal, it gets attenuated by 60 dB. So, the signal that leaks in is at minus 60 dBm. All right. So, in that case, what are you going to get at the output of the mixer? Well, you are going to get your signal at DC, and on top of it you are going to get the LO times the LO, which is 20 dB larger than the signal power. Okay, and that is also going to be at DC. Is this a problem? Does not look like it is a major problem, it is only at DC. Now, consider the fact that your local oscillator is not a perfect oscillator. The local oscillator, which is at 1 gigahertz, you think it has a frequency response that looks like this, right. You have impulse functions at plus and minus 1 gigahertz. Unfortunately, this is impossible to build. Okay. If it is a square wave, impulse functions at plus 1 minus 1 gigahertz, then at plus 3 minus 3 gigahertz, etc. Let us ignore the plus 3 minus 3, it is irrelevant. Okay. Also, I am going to knock off this negative portion, it is not really necessary as far as our understanding is concerned. This LO signal is impossible to generate. Why? You are always going to generate something which has noise, all right. It is never going to be a perfect local oscillator. It will be an oscillator and there is going to be noise along with it. Now, this noise, remember we have cut out the amplitude noise, this noise is called the phase noise. because that is all we have got over here. So, where the 0 crossing is, right, that determines the phase noise. It is not at the perfect place, it is a little bit off from the perfect 0 crossing. So, phase noise, as far as digital designers are concerned, they call it jitter. Clock jitter, right. So, where the 0 crossing is, there is a little bit of misalignment over there, and that misalignment is random. It varies from cycle to cycle. So, that is called clock jitter. It is the same thing, phase noise is the same as clock jitter. You can do the mathematics and work it out what is the exact relationship between phase noise and clock jitter, how much phase noise will give you how many picoseconds of clock jitter, etc., etc. Fine. So, there exists clock jitter, which means that the spectrum of the signal, when you look at the spectrum of the signal, it is never going to be that perfect impulse at your desired frequency. It is going to be something like that looks like an impulse, but never is going to be an impulse. It is going to be something which has skirts around your center frequency. All right. These skirts are because of phase noise, and phase noise is mathematically expressed in terms of how much this skirt is with respect to the center frequency at a given offset. So, suppose I exaggerate it, okay, and this is how the spectrum looks like. Then phase noise is expressed as so many dBs with respect to the carrier signal. This is the carrier signal. So many dBs with respect to the carrier signal, dBc per hertz at an offset frequency from the center frequency. So, at a 1 megahertz offset, I have got 80 dBc per hertz, less than the carrier, minus 80 dBc per hertz, that is my phase noise. Okay, this is just an example. So, now let us go back to our example. So, your local oscillator is never going to be this perfect signal. Your local oscillator really is going to look like this. And when you do LO times LO, what is going to happen? When you do multiplication in the time domain, you do convolution in the frequency domain, right. When you convolve this with this is the attenuated version of the LO, what do you expect to get? You expect to get the square of the LO, which is spread around. All right, and that is going to come on top of your signal. So, your phase noise is going to get squared by itself because of the mixer, and it is going to spread all over your signal. So, this can prove to be a disaster as far as your design is concerned. So, what do you have to do about your design? if you want to design a mixer for direct down conversion applications, what do you have to do? You have to make sure that LO leakage is minimum, so there should be no coupling whatsoever between the LO terminal and the RF terminal. So, they should be somehow isolated. I do not know how, you have to make sure of that. Place them far apart, do all kinds of things, make sure that CGD is not there, etc. All right. What else do you have to do? You have to make sure that phase noise of your local oscillator is minimum. Right? That also has to be taken care of. You have to make sure that phase noise is absolutely clean. There is no phase noise. So, all of this will come from the specifications. So, if the specification is as I said, then you have to make sure that even after the mixing of the phase noises, the amount that you get is less than the power that you have got from your signal. So, you need signal to noise ratio, power is coming from your signal, phase noise is mixing with itself, that is creating some noise. So, that signal to that noise ratio has to be very large, right. This is what you have to do as far as your mixer design is concerned. As far as your oscillator design is concerned, you have to make sure that the oscillator has superb phase noise properties, right. Can we proceed? All right. The next non-ideality is when the RF leaks into the LO. Is this a big problem? Is this a big problem at all? No, it is not a big problem at all, because the LO is a 1-0 signal, remember. The LO is a 1-0 signal. So, when the switch is off, it is off, when the switch is on, it is on, right. It is either completely on or completely off. That is why square wave helped us. So, over here either I get plus beta times something or I get minus beta times something, I do not get any intermediate values over here. Okay. The only time when the RF can actually leak into the LO and create a difference is at the transition edge. At that edge, if RF happens to mix into the leak into the LO, then I get some problems. Then RF mixes with RF and creates double the signal, the square of RF. Square of RF is definitely, first of all, RF is going to mix with RF with attenuation. The square of RF with attenuation is going to be much less than RF mixed with LO. So, you will get something down here compared to the RF itself. So, this is not that serious a problem as far as we are concerned, right. It is not that serious. What is serious as far as we are concerned is the LO leaking into the RF path. The LO is a large signal, it can leak easily get into the RF path. The RF is a small signal. When it leaks into the LO path, it becomes even smaller. The LO is gigantic compared to the RF. So, it is not really something which is very serious. So, we are not going to worry about it. What is worrisome for us is the local oscillator leaking into the RF path. What about in the transmit case? Same story. local oscillator leaking into the DC. When the local oscillator leaks into the DC, I get the square of the local oscillator with some attenuation. Now, remember that the local oscillator is not a perfect signal. There is phase noise associated with it, and when there is phase noise associated with it, I will get the square of the phase noise on top of the DC. Is this a problem? What does the output spectrum look like? At 1 gigahertz I have my signal. And the LO times the leaked LO is at DC. So, it is not going to cloud my signal at all. All right. So, this is not a terrible issue as far as we are concerned. If the LO signal looks like this, if the LO signal looks like this is not a terrible problem. If the LO signal happens to look like this, then this is still going to be a problem, right. There are times when the LO signal does look like this red curve with some DC, and that is when you make a ring oscillator. If you make an LC tank, inductor capacitor tank, and you make an oscillator out of the inductor capacitor tank, then typically this is not going to be the case. Your LC oscillator will have a characteristics like this, okay, in which case you are saved from this problem. However, if you have made a ring oscillator, then the LO will have a significant component at DC. There is going to be noise at DC, phase noise at DC, which means that that is going to become a significant problem as far as your transmit path is concerned. Okay. We will look at oscillators and this phase noise business and where it is coming from, and we will take a look at all of this, but this is just a prelude. Take it as a prelude to what is coming in future. Okay. So, we kind of understand the direct down conversion problem. Okay. LO can leak any time into the RF signal, and as soon as that happens, you get a DC offset, you also get phase noise problems. This seems like it is something which is unavoidable. Both of these problems are so hard to solve that it is almost intractable, right. And this is one of the reasons, these two problems are one of the main reasons why direct down conversion is discounted as a popular method, popular radio architecture. Okay. These two negatives as far as direct down conversion are concerned are so big that direct down conversion is discarded and in many cases thrown out. They are not options at all. So, typically what happens is that when your signal bandwidth is small, your signal bandwidth is so small that phase noise can easily cloud the signal bandwidth. Phase noise square can easily cloud the signal. in those cases direct down conversion is almost not possible as an architecture, as a viable architecture. We have to go for something else, right. In cases where the signal bandwidth is significantly large, typically these are CDMA kind of signals, CDMA, code division multiple access, right, WCDMA, wideband code division multiple access, WiMAX, that is time division multiple access, but it has a wide bandwidth. They do a lot of spread spectrum techniques, frequency hopping is there. Then OFDM, right, OFDM techniques are also used in WiMAX. The next one is 802.11, your standard Wi-Fi. Okay. There also the bandwidth is large, you are using OFDM, your bandwidth is fairly large, and when the bandwidth is fairly large, then the square of the phase noise is only a small portion of the total signal, which means that the signal is never going to be clouded by the square of the phase noise, because your signal is much broader, right. So, this is the basic idea, that if my signal has a wide band, then the square of the phase noise is not going to cloud me. I can use direct down conversion. Direct down conversion is a very simple architecture. You have the RF, you mix it with a signal which is with an LO signal which is tuned to the RF signal, and you directly go to baseband, and then at baseband you put a low pass filter, and then after the low pass filter you put your A to D converter and you figure out what has been transmitted, right. This is a very popular architecture when the signal bandwidth is large. So, systems like WiMAX, WCDMA, CDMA and 802.11, typical receivers in these standards will be direct down conversion. However, when you go for narrow band communication protocols, for example, GSM, okay. GSM is most widely used cell phone standard, or older stuff like amplitude modulation, frequency modulation, TDMA standards, older standards of TDMA, etc. If you talk about any of these architectures, direct down conversion is almost never used because of this intractable problem of LO leakage, phase noise of the local oscillator and so on. All of these cause problems because of the low bandwidth of the signal. This is traditionally called the DC offset problem. It is not necessarily at DC that it happens, but it is called the DC offset problem. So, because of the DC offset problem, DC is a large portion of the narrow band signal, right. DC and surrounding frequencies are everything that you have. So, that is why it is called the DC offset problem, and because of this problem direct down conversion is almost never used in standards like GSM. Okay. Then what is used? So, the most general radio architecture is something which is called super heterodyne, but before we go to super heterodyne, let me talk about heterodyne. So, let us do it by example. Let us say that my RF signal is at 1 gigahertz. Now, I am going to choose the LO signal at say a frequency of 0.9 gigahertz. When I multiply a 1 gigahertz signal with a 0.9 gigahertz signal, I expect two output frequencies. I expect something coming out at 1.9 gigahertz, something else coming out at 0.1 gigahertz. Okay. Of course, I am going to low pass filter this, and I am going to take the something which is produced at 0.1 gigahertz, right. This 0.1 gigahertz is the intermediate frequency, also called the IF. So, this is okay, I have not finished yet. This is almost what a heterodyne stage looks like. So, you have got the low noise amplifier, okay, there is something in between, we have not yet come to that, and that is coming from the antenna. From the antenna you go to the low noise amplifier, from the low noise amplifier you go to the mixer mixes with a local oscillator which is not exactly the RF signal, but close, and as a result it produces an intermediate frequency. Now, think of LO leakage. If the local oscillator leaks through, is there any problem? No problem, because when it leaks through it produces a DC and neighboring stuff, but I am not interested in DC, my signal goes to 0.1 gigahertz, right. So, I can easily cut off the stuff that is at DC. It is very easy to cut off DC and neighboring stuff, all right. The problem here is that not only will 1 gigahertz go to 0.1 gigahertz, if there is a blocker at 0.8 gigahertz, what is going to happen to that? The blocker at 0.8 gigahertz will also go to 0.1 gigahertz, right. If there exists a signal which the antenna picks up, a large signal, maybe your friend is talking to his friend at 0.8 gigahertz, right. That signal will also couple in and it will fall exactly at 0.1 gigahertz. Now, this is a problem because the blocker is falling on top of your signal, can't let that happen. So, what we put over here is something which is called an image reject filter. The job of the image reject filter is to keep your desired signal and to get rid of the blocker. Okay. If your local oscillator is at 0.9 gigahertz, if your signal is at 1 gigahertz, then the image reject filter should be a filter that cuts out 0.8 gigahertz, allows 1 gigahertz through. Something like this, all right. Now, how difficult is such a filter to build? It is impossible to make a brick wall filter, no surprise, right. The image reject filter is some sort of a band pass filter, looks like some sort of a band pass filter, and Q, the quality factor of this band pass filter, is the ratio of the center frequency to the bandwidth. If I want the bandwidth to be small, then I need a large Q. Large Q is very difficult to build. Okay. So, the lowest bandwidth that the largest bandwidth that I can allow is something which is around, let us say, 100 megahertz midpoint between 1 gigahertz and 0.8 gigahertz separation. The midpoint of that is 0.9 gigahertz, which has a separation of 100 megahertz. So, that means that I can allow for a bandwidth of 200 megahertz, which means that the Q of this band pass filter is about 5, which is not very difficult to build. All right. So, what does this tell you? This tells me that this local oscillator over here can't be very close to the RF signal. It needs to be a little bit away from the RF signal. If the RF signal is at 1 gigahertz, LO can be at 0.9 gigahertz. That will give me a Q of 5 for the image reject filter. But if I want my LO to be at 0.99 gigahertz, then I need a Q of 50, which is very hard to build as far as the image reject filter is concerned. So, the intermediate frequency will be a significant fraction of the original frequency. So, here the intermediate frequency I have chosen is 0.1 gigahertz. If I wanted 0.01 gigahertz, then LO would be 0.99 gigahertz, then my Q would be this frequency divided by the IF frequency by 2 or so. So, that will be the Q of the image reject filter that you need. So, large Qs are very difficult to get. So, you make something with a small q, right, which means that you need your IF to be a significant fraction, maybe 1/10 of your RF. Now, that is probably no good, because if I want to put my A to D converter, if I want to put my low pass filter, then this is no good. I mean, I can't do A to D conversion at 100 megahertz, it is very hard, right. I would rather do it at 10 kilohertz or 100 kilohertz, not at 100 megahertz. So, you put another stage. So, you put another image reject filter, okay. You put another mixer and you put another LO. Let us say now you choose your LO to be 90 megahertz. Image reject filter to cut out 80 megahertz and allow 100 megahertz. Okay. So, you have got your IF. Now, your IF, your second intermediate frequency is at 10 megahertz. So, you have got a second stage, then you can go for a third stage and so on and so forth. Then you have got 1 megahertz, right. So, this in general is the super heterodyne radio. This entire scheme of things, you make one heterodyne stage, you use the heterodyne stage as a building block, step by step you go down in terms of frequency. Every time you generate one local oscillator, you have a mixer and you have an image reject filter, right. You will need 3 local oscillators here running at 3 different frequencies, it can be done, trust me, it can be done. Okay. I have 3 different oscillators at 3 different frequencies, you can make all of these frequencies and make this, it will work, there is no problem. This is the most general radio architecture, radio receiver architecture as I have shown over here. Alright, it is called the super heterodyne radio, and person attributed for this work, his name is Edwin Howard Armstrong. So, I should mention a brief, give you a brief, very brief history about this gentleman, Edwin Howard Armstrong. He is the last of the solo inventors. What is solo inventor? Solo inventor is, the era of Edison and Faraday and Tesla, one man inventing something. We do not have that anymore. Nowadays companies build something, they no longer invent anything to start with, they build some product. A team of engineers develop a certain product, iPhone and iPad and just the cell phone itself or anything that you are talking about, the computer, it is made by a team of engineers. So, this invention word has gone. So, Edwin Howard Armstrong was the last of these solo inventors, and he was an engineering student, electrical engineering student. As a student, he developed, those were the early days of the radio. Okay. At that time people did not know what is going on and there was complete lack of understanding of the entire subject. Maxwell's laws were not even there, right. So, at that time he invented the regenerative amplifier. So, he made an amplifier with vacuum tubes etc., and this used the concept of positive feedback and could amplify a very small signal into a very large signal. So, this he did as an undergraduate student, and then as a graduate student he developed this super heterodyne radio architecture. This work that I showed you today was developed by this gentleman as a graduate student, and then he became a professor and he invented FM radio, the entire basis of FM radio, right from the mathematics to building the transmitters, building the receivers, as well as wide scale distribution of these transmitters and receivers, right. All of this was done by him, and at that time he was a professor. So, undergraduate, then graduate and then professor. This work was done as a graduate student. Okay. So, that is your super heterodyne receiver. We are going to stop this as in we are going to pause and we are going to carry over from next class with this note. We have now developed some understanding of radio architectures, how the mixer fits in, where it fits in, and why radio architectures kind of revolve around the mixer. Okay. So, with this note we are going to stop and we are going to carry forward in the next class. Thank you.